Hello, everyone. Welcome back. Um, Dan could not be here with us today, so he instructed us to just kick things off a few minutes after 12. So I do believe we have 31 folks present. I think that's the majority of us. So let's just get into it. My name is Meredith, and I will be one of your moderators today. Um, we will be doing things a bit differently this time around, and also for our next meeting as we transition into presentations by our first year graduate students. This meeting and the next will feature 5-minute student presentations. The last time we met, we heard from Emily Blackwood, who is using virtual reality to reconstruct archaeological sites on the Peruvian coast, and also by Matt Farragher, who is investigating the effects of dissolved organic carbon on lake ecology in Acadia National Park. And to further summarize Emily's presentation, I will pass things over now to Paloma.
Thank you, Meredith. So last week we heard from Emily Blackwood, and she is using virtual reality technology to create a computer-generated, immersive, and interactive visualization of the Ostra collecting station on the north central coast of Peru. She's piecing together all the information available from excavations dating back to the 80s and 90s, as well as drone footage and Google Map images in order to create a representation of what the site may have looked like while occupied 6,500 years before present. One major change is the shoreline, which was much closer to the site in the past, occupying the area where beach ridges are now. The purpose of the site was thought to be defensive because of the presence of slingstone piles and pearls. The virtual reality experience will allow the user to step into the perspective of someone who may have occupied the site by giving the user the average height the residents were thought to be at the time, and to allow better visualization of the archaeological record.
Thanks so much, Paloma. And now we will turn it over to Lizzie, who will summarize Matt's presentation.
Thank you, Meredith. So Matt's research on vertical phytoplankton gradients from under ice to open water in lakes of Acadia National Park focuses on the dissolved organic carbon concentrations of lakes in Acadia National Park. And DOC is a group of compounds created through the decomposition of terrestrial organic matter. These compounds can travel from land to lakes and streams where they can alter the color and temperature of water. Matt studies DOC concentration in lakes to understand the ecological consequences of environmental change, and to investigate the effects of DOC on lake ecology. He focuses on the vertical habitat gradient of lakes, the vertical destruction of organisms within a lake in response to environmental changes. 4 lakes in Acadia National Park were sampled through the ice in February 2020 and bi-weekly from May until November the same year. Matt measured the vertical profile of chlorophyll efflorescence, a proxy for relative algal biomass. And Matt also collected water samples from 3 different depths and filtered them for extracted chlorophyll biomasses and recorded Siki depth for each lake. Matt's results have shown that higher DOC lakes had more vertical heterogeneity and greater seasonal variability of chlorophyll profiles than low DOC lakes, and despite overall concentrations. Diverging DOC concentrations in northeastern US lakes have large impact on ecological conditions and the vertical distribution of phytoplankton. So Matt's next step is to understand the ecological consequences of long-term changes in DOC concentration. Thank you. And now I think that Emma will introduce this week's speakers. Thank you.
Thanks, Lizzie. So as Meredith mentioned beforehand, this week we're doing shorter talks. We're going to hear from 5 different first-year graduate students today. We'll hear from Hanna Brooks, Carly Frank, Matthew James, Mark Jordan, and Bailey McLaughlin. First up, we have Hanna Brooks, who is going to talk about pollution tracing in the North Pacific, a lead isotope story from Mount Hunter, Alaska.
Hannah, I think you're on mute.
Sorry. Is that better? Okay, great.
Yes.
Sorry, it's been one of those mornings. My name is Hanna Brooks. I'm a PhD candidate working with Carl Kreutz and others in the Climate Change Institute. And my project is looking at lead isotopes from Mount Hunter, Alaska. And so, wow, welcome to technology. Imagine that this is a lovely video from NASA that is showing you the wind patterns across the globe. I don't think it's going to play for me, but it's not worth it in a 4-minute talk. The wind pattern from Mount Hunter actually is bringing wind across the Pacific from China. And so when we're looking at lead pollution in the North Pacific, what we're actually seeing is a signal from China and the rest of Asia. And lead is important. It has now been discovered that lead is important, and adverse health effects from lead are critical at any amount. And so it is important that we understand exactly what the lead emissions are as they come over from the Pacific, from Asia. So how does lead get into the atmosphere? So as we have emissions from manufacturing and from our automobiles, lead is released as aerosolized particles, and these are picked up and transported along with dust and sea salt spray into the troposphere and stratosphere, and they can be transported for very long distances, sometimes up to hundreds of kilometers, which would bring them across to the North Pacific. So this project examines the emerging story of pollution deposition in the North Pacific. There are 2 ice cores already, which have really examined this rudimentarily and gotten a pretty good idea of what's going on so far. We have the Mount Logan record, which extends past the last 8,000 years, and then we have the isotope record from Eclipse, which shows us the last 150 years. And with the ice we have on hand from Mount Hunter, sorry, we can extend this record back throughout the entire Holocene. And this is important because China actually phased out their leaded gasoline in 2001. And so neither the current Mount Logan or Eclipse records show what happens after China phased out their leaded gasoline. And we currently have Mount Hunter ice all the way through 2019. And so being able to extend this record both forward in time and back in time will allow us to have a better idea of how the North Pacific is responding to Chinese emissions. Additionally, the first recorded Chinese smelting happened about 5,000 years before present. And so really taking an examination of some of these more ancient signals is a critical part of this project. So finally, these are some of the guiding research questions as I delve into my PhD. So can we see pollution signals from ancient Chinese civilizations? Can we reproduce the signal from Mount Logan and Eclipse at Hunter? And if not, are these differences explainable? How have emissions changed since the phase out of leaded gasoline in China in 2001? And lastly, we have the potential in COVID-19 to allow us to uniquely test modern trajectory and transportation questions due to the change in manufacturing in China. So the possibility of a COVID snow pit is quite alluring. So thank you so much.
Thank you, Hannah. So we have a few minutes for questions if anyone has any questions for Hannah. Go ahead and unmute.
Yeah, Hannah, I'll ask you a question. I'm wondering, so since the phase out of leaded gasoline, what are the major contributors to lead from China right now?
Yeah, so it's a bit of an uncertain question, but particularly the manufacturing of industrial products like cement produce a lot of lead. And just after the phase out of tetraethyl lead in gasoline, unleaded gasoline and diesel both also have lead in them. They are estimated to produce about 8% of the current anthropogenic lead emissions. So there are still lead emission signals coming from automobiles, even though we've phased out leaded gasoline.
Wow, really interesting. Thank you.
Yep, and we have time for a couple more questions if anyone wants to unmute.
This is Alex. I was just, I looked at the Logan record in comparison to the European record in the past for lead. And it's interesting that if we zoom in to the last 50 years or so, maybe 80 years, we see a decline in Europe, obviously due to changes in emission laws, and rise in China, which of course you know. And it's not just the gasoline, it's also all the smelting, all the recycling is all moved to Asia, all of it. All of the there are no more smelters in Europe except one in Sweden that actually recycles batteries and supposedly very well controlled, although the people around it aren't particularly happy about it. So there is really a correspondence or a mirror image between the two records and in that evolution. So it'd be very interesting to see what the health outcomes have been for people since 1970 due to even small amounts of lead exposure, which have been found since about 3 years ago, even in adults, to cause enormous increases in death rates, particularly in the US, 500,000 deaths in cardiovascular diseases due to very low lead exposure in adults. We knew about children, but now we know about adults too. So there's a substantial story there.
Yeah, it's very interesting. Of the industrialized countries, China is the only one who is even self-reporting that they have an increase of lead emissions since the phase out of leaded gasoline. And it's pretty marked in the increase. So there's definitely something going on. But with all of the records ending at roughly the time that their phase out happened, it's very hard to know exactly how well their self-reported emissions are lining up with the reality.
I have a question. I'm sorry, I logged on 5 minutes late. But one question I had was, what is the state of the glaciers that you would be studying? I mean, I know other Asian glaciers, we've lost the top 200 years. So how would you replace the most recent years of deposition?
So this is from Mount Hunter in Alaska, and we currently have ice in the freezer through 2019. But yes, the loss of the melt loss in Asia is very bad. And there's actually a bunch of funding that China in particular just did, where they're just going out and drilling. They're not even analyzing, they're just drilling cores as fast as they can to try to just get things in the freezer and preserved. So the preservation on Mount Hunter at the moment has not been affected by climate change as much as some of the cores in China have been.
Well, I look forward to seeing this. Thank you so much.
Yeah, thanks again, Hannah. I'm going to pass it over to Emma to introduce our next speaker.
Sounds good. Next up, we have Carly Frank, who's going to give us a short intro on assessing heat stress and drought impacts on the Maine blueberry production.
All right, let me just share my screen. Okay, we can all see this? Yep, all right, and I've been having some internet issues for, if some reason, you can no longer hear me or something, please somebody tell me so I don't just start talking to myself. All right, now let me just minimize myself so I don't see myself talking. Okay. So hello, for those of you who don't know me, my name is Carly Frank. I am a first-year master's student in the Climate Change Institute, and I'm also part of the One Health and the Environment NRT, which I'll go into a little bit in a second. I'm advised by Dr. Sean Burkle, Sandra Dayers-Stone, and Lily Calderwood. And as it was introduced, my research will focus on assessing heat stress and drought impacts on Maine blueberry production. I am just beginning the research, of course, so things will most likely change a little bit. So as I mentioned, I am part of this One Health and the Environment NRT, which is a new program and involves quite a few departments. It's very interdisciplinary. And I wanted to stress this because it involves both a social science and a biophysical portion, which you'll see as I go through my presentation. But the NRT stresses the idea of a One Health concept, which is that the health of humans, animals, plants, and the environment are all linked, and that addressing the connections between them is essential for the health of all organisms. The concept is used to solve countless plant, animal, and human health and economic issues that arise as the climate and ecosystems change. And this figure on the right is just a visual representation of the One Health concept and how everything, of course, is interconnected. So my thesis research objectives will involve, like I said, a physical science and a social science component. That physical science component deals with characterizing recent changes in climate most relevant to agriculture, as well as examining relationships between climate and available crop data. For the social science portion, I'll conduct surveys of Maine landowners, as well as migrant and seasonal workers to gauge climate change risk perceptions of the blueberry sector and if and how these perceptions vary by group. And then I hope to integrate both components to facilitate future decision making. So for that physical science component, I'll be doing a climate analysis, which I've further broken down into a historical and future components. For the historical analysis, I'll analyze changing conditions across Maine from 1981 to 2020 using daily and monthly gridded data from PRISM, which includes a wide variety of variables. And then from that, I will develop time series and maps for annual growing degree days and high heat index, annual growing season length, which will be based on first and last frost dates, and drought indices, specifically SPEI, which is standardized precipitation evapotranspiration index, which is actually already available on the PRISM grid from the Western Region Climate Center. And then for the future component, I'll be developing plausible future scenarios for 2050 and 2100 for Maine blueberry crops based on historical analysis and future projections. And these products will be freely available to those who are interested through the Maine Climate Office. Moving to the social science component of the research, I'll be conducting two separate surveys. I'll use a short one-page survey intended for landowners that will be handed out on paper at summer field meetings, which will be organized by the UMaine Cooperative Extension. This survey will collect demographic information and gauge climate change risk perceptions. And then I will also use an in-depth survey, which is aimed at Maine migrant and seasonal workers. And because it's more in-depth, I have the ability to use the van der Linden model, and I'll also add trust. And then I have a brief figure on the next slide that'll hopefully clarify that. And then additionally, the survey will seek to understand ways in which working conditions could be improved to accommodate the changing climate, as well as possibly including questions relating to food security. Then, as I mentioned, this is just a visual representation of the van der Linden model, which serves to measure risk perception. It takes into account cognitive factors, experimental processing, sociocultural influences, and sociodemographics. And then I will be including trust as well. So in summary, I'm hoping to increase baseline understanding of climate impacts on agriculture through historical analysis and develop plausible future climate scenarios for blueberry production. These resources will be made available to stakeholders through the Climate Change Institute Maine Climate Office. I also hope to improve understanding of specific drivers of climate change risk perceptions and how perceptions may vary between landowners and migrant and seasonal workers. And then doing so will enable better communication, which will hopefully lead to an increased risk perception, which is linked to an increase in willingness to implement adaptation strategies, ultimately promoting resilient agricultural systems and gaining more support for action. This also has the potential to lead to better working conditions. So thank you all for listening. I'd like to thank my advisors and of course NSF for funding this project, and I'm happy to answer any questions that anyone might have.
Thanks so much, Carly. Does anyone have any questions?
It's Andre. I have a question. Carly, when you're going to do projections for 2050 and the next century, will you consider changes that people call rapid climate change events or abrupt shifts in climate? Or are you going to assume that everything will increase steadily?
That's a great question. It is hard being that I'm so early, still trying to plan everything out. I think ultimately the plan is to do like steady scenarios opposed to rapid shifts, but nothing has been fully decided yet.
Thank you.
Hi, Carly. This is Elizabeth LeClaire. I was wondering about your interviews on risk perception and if you will kind of be going on like kind of self-imagined risk, or if you'll be kind of digging into vulnerability and resilience as components of risk.
Yeah, great question. Of course, again, we're still trying to iron out a bunch of things, and I don't come from a social science background, so I'm also very quickly trying to learn everything that goes into risk perception. So I don't have a great answer for you. I'm so sorry. But I think more so based on like those things I mentioned, like people's knowledge and the types of knowledge, as well as personal experience, where they're getting their information from, are the people around them influencing how they're thinking about climate change and things along that line.
Cool, great. Just so you know, I'm working on my dissertation proposal right now that's going to involve some things with risk and vulnerability more prehistorically, but I'm happy to connect with you and share any resources I find. I have a few now, if that would be helpful.
Yeah, that'd be great. Thank you. I appreciate that.
All right, thank you, Carly. I think it is time for our next speaker. Next up is Matthew James, who's going to give us a brief intro on Roke Island Group and Holmes Point, a comparative study of archaeological ceramics in Down East Maine.
There we go. Can you guys see that? Great. All right. So I'm Matt James. I'm a first-year graduate student in the Quaternary and Climate Studies program. And today we'll be discussing my thesis, which centers around a comparative technological study of indigenous ceramics from locations in Maine. Before I begin, I'd like to mention the University of Maine's land acknowledgement, and in addition, acknowledge the Passamaquoddy tribe for their support of archaeological excavation on their homelands. So studies of indigenous ceramics in Maine and the Canadian Maritimes has generally been underrepresented in archaeological research. The last major framework for analysis was Peterson and Sanger's 1991 An Aboriginal Ceramic Sequence for Maine and the Maritime Provinces. This article was the most robust framework for analysis of ceramics to date, but the scope didn't really allow for room for inclusion of regional variations. So my research is centered around two main goals. One, to corroborate ecological models of the past and to determine to what extent plant ecology affected ceramic manufacturing in a unique ecological region, and 2, to provide insight to technological variation within Peterson and Sanger's 1991 framework. So particularly, I will be looking at alternative tempers used in ceramics before firing, which are outside of the commonly accepted tempers discussed in their framework, which are grit and shell. So in 2019, Dr. Bonnie Newsom and I discovered impressions of what appeared to be balsam fir needles within the matrix of ceramics from Holmes Point West. These impressions were always found in addition to one or more of the commonly accepted tempers found in the Northeast, and were therefore still datable through stylistic and technological analysis. And we concluded that based on the distribution within the ceramic matrix and within multiple ceramic periods, that the inclusion of balsam fir needles was likely intentional. These images on the screen now depict a very diagnostic sherd from Holmes Point with numerous needle impressions found within it. The largest one is highlighted in red, and then magnified in images 2 and 3. You can see when compared to a balsam fir needle that the fine clay used in manufacturing of the pottery was able to pick up minute details from the needle itself, which subsequently was burnt or decomposed out of the ceramic. So Holmes Point and Roke Island are both located in what is referred to as a maritime spruce fir forest. This is a section of the Maine and Canadian Maritimes coast that's dominated by spruce, balsam fir, and blueberries and feather moss. And Washington County, Maine is a very diagnostic section of this ecoregion. And it's also home to a number of archaeological sites. Holmes Point is in Machias Bay and is also the location of UMaine's MAPI Field School program, and has been managed by Dr. Brian Robinson previously, and currently managed by Dr. Bonnie Newsom. Then 10 miles to the southeast is Roke Island, which has numerous archaeological sites located across the islands. And these were excavated mostly in the 80s. Temporally, my focus is mainly on the middle ceramic periods 3, 4, and 5. You can see in this table the dates from which those spread. And this breakdown was made again by Peterson and Sanger in 1991, and has been kind of the outline for analysis of dated materials in Maine from the past 3,000 years. So in widening my research outside of just Holmes Point, I quickly realized that there would be a number of constraints. One, that the span of manufacturing in the area only lasts 4,000 years. 2, that some sites only have a limited number of sherds or pieces of pottery. Sometimes the occupation of a site does not match up with the ceramic periods that I'm focusing on. And also the geographic area is fairly limited for where balsam fir is very diagnostic in relation to these archaeological sites. Fortunately, ecological models have shown that that the spruce fir forest has existed in Maine for the entirety of the time that ceramics have been produced here. And additionally, this is a very diagnostic area, so it's perfect for this kind of research. Analyzing this in the future will really allow for more analysis of manufacturing techniques for ceramics, and also potentially create a clearer picture of how climate and ecology shapes human practices, and particularly ceramic manufacturing. So thank you, and I'd like to acknowledge the Maine Academic Prominence Initiative, the Passamaquoddy Nation, and Doctors Bonnie Newsom, David Sanger, and William Belcher for their contributions. Thank you.
Thank you, Matt. So we can take about a minute for questions if anyone wants to shout out.
Hi, this is Elizabeth LeClaire again. I have a question for you, Matt. I was wondering if there are any hypotheses why the plant matter was added to the temper, what benefits that provided?
Yeah, in our 2019 article, we had started thinking about this. It's definitely not something that we're sure of. Some experimental archaeology might actually be the best way of figuring out what it was used for. It is potentially something to create a more temperature controlled vessel when it's fired. So having the air pockets in it could potentially allow for better control of water temperature in the vessel for keeping it hot or cold longer. And there are other reasons it might be included. And I have done a little bit of experimental archaeology with this and found that the ceramics are actually quite resilient when they're fired with these balsam fir needles inside of them. So it was definitely something that was not a negative when they used it.
Thanks.
All right, thanks, Matt. I think it's time for our next speaker. So next up, we have Mark Jordan on modeling river restoration projects.
Thanks. Hello, I'm Mark Jordan, a graduate student working with Peter Coons. Our research focus is fluid-solid interactions related to river hydrodynamics, sediments, river ice, and nature-like restoration structures. The research is an extension of the work Nick Richmond, Peter, and others undertook of the Penobscot River. The Atlantic salmon is an endangered species. Its survival is dependent upon many factors, including quality river and stream habitat. For much of the Atlantic salmon's traditional habitat has been severely degraded by historical log drives, dams, bridges, and culverts. The Narraguagus River was once a trophy salmon river, but the loss of habitat required for egg laying and the survival of the young has likely contributed to the large reduction in the river's salmon's population. Project Share, a conservation organization that works primarily in Down East Maine, has installed numerous river restoration projects on the Narraguagus River. They are currently working on restoring salmon habitat on a section of the Narraguagus River downstream of the Route 9 bridge, as shown on the right. For reference, Orono can be seen on the left. This is a picture of the Narraguagus River restoration site taken last summer. In case it's not obvious, this is not good salmon habitat. One of the problems here is that the riverbed is armored with cobbles and small boulders. What most likely was here prior to the log drives were accumulations of large wood, deep pools, and gravel riffles, which are key components of salmon habitat. Although Atlantic salmon is our target species, our overall goal is to reestablish the natural geomorphic and biological processes that produce quality habitat for salmon and our other native aquatic organisms. Reestablishing the natural geomorphic processes in the rivers typically involves putting back into the river the large wood and boulders that were removed from the river to enhance log drives and navigation. Over the last several years, nature-like engineered log jams and similar river restoration structures have been built on the Narraguagus and Monecticut rivers in Maine. Unfortunately, many of these nature-like structures have been severely damaged or destroyed by river ice. Therefore, we need to learn to design and build ice-resilient structures. The design process needs to start with an understanding the river's ice forces that the structures are subject to. Because direct measurement of river ice forces is impractical and unsafe during ice jam breakup events, we need a different way to approach this part of the design. Computational fluid dynamics, also known as CFD modeling, has been used to evaluate fluid-solid interactions in many applications, from offshore windmill platforms to bird feathers, and has a strong potential to provide insights into the interactions between river hydraulics, ice, sediments, and restoration structures. An example of a simple restoration structure and its fluid-solid model is water flowing over a set of logs in a stream. A model set up for this scenario might look like this slide. Traditional CFD modeling uses a grid or mesh approach that does not capture the chaotic water surface and resulting forces that are often associated with river hydraulics and restoration structures, as shown here. I developed this two-dimensional simulation of water flowing over a set of logs using a modeling approach known as smooth particle hydrodynamics, which is a meshless particle-based modeling technique. Smooth particle hydrodynamics, or simply SPH, is a relatively new, innovative approach to modeling complex hydrodynamics. SPH has recently been used to successfully model coastal structures impacted by ocean waves, including the interactions between floating and fixed objects. My hypothesis is smooth particle hydrodynamics can accurately model the interactions between four factors: river hydraulics, ice, sediments, and river restoration structures. If successful, SPH will allow us to design more ice-resilient restoration structures, help ensure that these structures create the appropriate habitat and be applicable to numerous northern rivers. The Narraguagus River Restoration Project will be used as a case study for my research. Key components of the project will include numerous boulder clusters, nature-like log jams, constructed wetlands between the log jams and the river's bank, and reconnecting the floodplain streams to the main river. Thank you for listening. I'm happy to answer any questions.
Thank you, Mark. So we have, about a minute for questions. We're a little over time, but that's okay.
Yeah, Mark, this is Paloma. Thank you. This is really interesting. I was just wondering if you could say a little bit more about what you mean by meshless.
So in a traditional CFD modeling, you take the area you're going to model and you divide it into typically a bunch of little cubes or rectangles that are, if you remember calculus, those dx's and dy's, well, each one of those little cubes is a dx and a dy. And then you solve the equations for everything usually it's on the nodes at these intersections, and just come up with a whole bunch of equations that you then solve numerically. And so it's that mesh, it's that breaking up of the object you're modeling.
Thank you.
Hey, Mark, the features that you're in the Narraguagus, for example, are you using like structure from motion to kind of map out their structures and trying to import that into your models in the future? Is that part of the plan?
We did a drone flight earlier on, and we couldn't get the resolution to be able to use the structure from motion. It would be great if we could get the quality of imagery to be able to then process it to pick up better detail of the riverbed. But of course, there's the problem with the reflection off the water. So ultimately, we had to go out and actually field survey the river itself and then use a 1 meter DEM for the floodplains.
Cool.
All right, thank you, Mark. Next up, we have Bailey McLaughlin on the places they'll go, a quantitative macroecological assessment of tree species range shifts.
Thank you. Oh, it looks like I can't yet share my screen.
Okay, for some reason I lost Stop sharing. There, I got it. Sorry.
No, no problem. Okay. Okay. Okay, can everybody see the full screen picture? Okay, great. Let me just adjust. See the box. Okay. Well, hi, everybody. Thank you for the introduction. My name is Bailey McLaughlin. I'm an ecology and environmental sciences graduate student with an affiliation in the Climate Change Institute. And I work with Brian McGill, and I'm going to use my 5 minutes today to talk about the first chapter of my dissertation, which is broadly about species range shifts and responses to global change. So I'm a biogeographer and macroecologist, and I'm primarily interested in big questions about biodiversity and global change. And one of the primary lenses I tend to think about how these topics intersect is through species distributions or ranges as they exist on the landscape. But what exactly is a range? Well, there's a range of potential ranges we might define and consider depending on the context of the questions that we're asking. And so for my purposes here, I consider species ranges in two primary contexts, where they exist in geographic space and where they exist in associated environmental space. And for both, I think about this at biogeographic scales that capture all or most of a species distribution. So we can take a species, any hypothetical or real species, figure out where it exists on the landscape, map those in geographic space, draw polygons around them to get the geographic range extent, and then we can couple that occurrence data with environmental data associated with each of those sites to characterize the conditions in the sites where the species occurs, thus being able to map it in environmental space. And so what the range ultimately boils down to then is this measurable entity that we can use to learn about how species relate to their environments. And so the range is this fundamental unit of ecology and biogeography, which becomes a really useful tool when trying to understand things like what I started out with, how biodiversity or species are going to be impacted by or respond to global change that might alter some of these environments. And so if the range is a useful tool to understand potential responses, the next question becomes, well, how might species actually respond to global change? And so a useful framework to understand potential ongoing and future responses to change emerges from consideration of what we know about how species have responded in the past and also in the present to changes, which I've visualized here in this schematic. So in the top, we see a species in its current range, which is represented by the green circle. And then at some future time step, the conditions in that current green range shift to where that red circle is above it. So if we overlay a climate change scenario on that top panel, we can then monitor how the species might respond in the context of those changes it's faced with. So it might do just fine and stay put and tolerate the new conditions. It might have to adapt in some way to be able to persist in place. It might migrate to track that suitable habitat and ultimately shift its range to the red circle. And if it can't do any of those other three, it might end up going extinct or locally extirpated from sites. And so with this response mode framework as kind of a guide to understand how biodiversity and global change might intersect, and the range is this important tool to understand these responses, my dissertation work focuses in on, and this first chapter especially, focuses in on this migration range shift route, which I hope in so doing I can start to understand when some of these other patterns of responses might be more likely for different species. And so folks have studied ranges and range shifts for a long time, but there's a couple things still lacking in that literature. One is an understanding of the fundamental processes that set range limits and ultimately dictate range boundaries. And the second is an understanding of range shifts on shorter timescales than what we typically assess. So we typically project forward into centuries or sometimes back into millennia, but what we're missing are kind of decadal scale changes, which brings me to this question that kind of grounds the first chapter of my research. What processes underlie geographic ranges, and how can we monitor range shifts on shorter, more policy relevant timescales? So to address this, I propose using species ranges partitioned into distinct life stage components, so juveniles and adults, for example, to start to assess range shifts on generational timescales that we're seeing birth and death dynamics readily play out on the landscape, because it's ultimately birth and death that decide, so to speak, where those range limits exist. Because successful regeneration is critical for something to be able to persist in place. And we can use trees as a model taxon to look at these dynamics because of their unique life history strategies and their distinct life stage classes of adult, sapling, and seedling. So I'll partition a tree's overall range into its 3 life stage components to try to understand range shifts at large scales. And so I'm led to two main predictions about what might happen if we take this approach. The first is that the processes that lead to a range shift can actually be snapshotted in time by looking at the range broken down into these distinct life stage components. And then the second is that among species within the data set, we'll see differences in how these ranges, or in differences between these life stage ranges, because we don't expect range shifts to be uniform in direction or magnitude, for example. And so to ultimately test these hypotheses, I'll first consider a range shift as a change in range size, a change in the position or distance between 2 range centroids, and then the directional movement of a range shift between distinct intervals. And so you might have guessed, but the distinct intervals that I'll be using here are life stage classes rather than time per se. Life stage can serve as kind of a proxy for time. So we'll have seedling, sapling, and adult components that I'll break the range down into. And the data I'll use for this comes from the US Forest Inventory and Analysis database. And I'll look at all tree species contained within the contiguous US. And so if we combine these ideas, what we might see, some hypothesized realizations of what a range shift might look like broken down into these components, are in this bottom image here. So we might see no change because the life stage ranges are really nested and there's recruitment happening in all areas of the adult range. Or we could see expansion, contraction, and multi-directional shifts potentially. So the ultimate goal is to take this quantitative approach to studying range shifts to ultimately, hopefully, observe incipient range shifts as they're happening on the landscape. And when they're not, try to start to understand some of these other response modes that might be more likely. And so this work is focused on the geographic range, but I plan to extend it into that environmental space component that I mentioned at the start, as well as a few other directions. And this work really adds to and expands on a budding literature that considers life stage differences between species. So I'd be happy to talk more about that if anybody's interested also. But I think that's all I have. So thank you for your attention, and thanks to everybody who's helped along the way.
Thanks so much, Bailey. Does anyone have any questions?
Hopefully I stopped sharing my screen now. Okay, cool.
I just thought of a question. I'm curious if you have particular tree species in mind, or if you're looking at kind of particular natural communities of trees, or yeah.
So my goal is to look at all or as many of the US tree species as possible, just because I think as large of an assessment as we can get can try to chip away at some of the general patterns that might exist in the data. So my goal is to study all of them, but as this continues to take shape, potentially that might have to change a little bit, but yeah, no specific answer to that, because I guess the answer is everything.
Cool, thank you.
Okay, if we have no further questions for Bailey, well, first, well, just since we're all here, does anybody have any announcements they would like to make to our community? Okay, well, thank you all for joining us for this week's Born Symposium. And also thank you to all of our presenters who presented to us this week. Unfortunately, like I said, Dan was unable to meet with us this week, so we are left without his clever closing remarks. That said, thank you all again for tuning in, and we hope to see you at our next meeting, which will not be next week. It will be the following Monday on February 22nd.